Hello everyone, this is Shri Guru over here. In the previous video, we discussed experimental study of photoelectric effect. In that, we have studied various graphs. And also, we studied the laws of photoelectric emission. In this video, we are going to discuss about the Einstein photoelectric equation. Einstein explained the various laws of photoelectric emission on the basis of Planck's quantum theory. According to Planck's quantum theory, light radiation consists of a tiny packets of energy called quanta. One quanta of light radiation is called photon, which travels with a speed of light, that is 3 into 10 raised to 8 meter per second. And the energy of the photon is given by E is equals to h nu, where this h is a Planck's constant and nu is the frequency of the light radiation. Einstein assumed that one photoelectron is ejected from a metal surface if one photon of suitable light radiation falls on it. Let a photon of light of energy nu incident on the photosensitive surface. The energy of the photon is spent in two parts. A first part of energy is used to liberate the electron from the metal surface, which is equal to the work function phi naught of the metal. The second part of the energy is used to photon is used to imparting the maximum kinetic energy to the emitted photoelectrons. This means if we consider this is the 100% energy of the photon, which is used in two ways. A part of energy is used as a work function, which means that energy is spent to liberate the electron from the metal surface. To overcome from the metal surface, the energy is spent. That remaining energy is providing kinetic energy to the liberated electron. If we consider V max is the maximum velocity of the emitted photoelectron and m be the mass of the emitted photoelectron, then the kinetic energy is given by K max is equals to half mv square. According to Einstein, if this is the h nu is the energy of the incident photon, which is used in two parts, this is known as a phi naught, which is nothing but work function. The plus this is half mv square, that is kinetic energy to the emitted photoelectron. This is the Einstein equation. If we rearrange this, we will get this equation: K maximum, that is 1 divided by mv square, is equals to h nu minus phi naught, which is known as Einstein photoelectric equation. The incident photon is of a threshold frequency V naught, then the incident photon energy h nu naught is just sufficient to eject the photoelectron from the metal surface without imparting it any kinetic energy. This means the incident photon energy is exactly the required frequency nu naught, which is just required to liberate the electron from the metal surface. And the energy of that incident photon is h nu, which is completely used to liberate the electron from the metal surface. Therefore, h nu naught is equals to phi naught, which is another work function. If I substitute this equation in the previous, in this equation, then we will get half mv square h nu minus h nu naught. If we take h common, we will get h into bracket nu minus nu naught, which is also known as Einstein photoelectric equation. Explanation of laws of photoelectric emission. By using this equation, Einstein explained the experimental study of photoelectric equation. According to him, the intensity of the light is increased, the number of incident photon also increases, therefore emission of ejection of photoelectron also increases. This means that intensity is nothing but number of photons incident on the metal surface per second. That means as much as the number of photon increases, the liberation of photoelectron also increases, therefore photoelectric current is also increases. The second one is if nu is less than nu naught, the photoelectric emission does not take place for the incident radiation below the threshold frequency. As we have discussed in the graph, there is a minimum frequency is required to liberate the photoelectron. If in this equation V is less than nu naught, then kinetic energy becomes the negative. Therefore, kinetic energy cannot be exist in a negative value. Therefore, this is not possible. Third, if nu is greater than nu naught, maximum kinetic energy of the photoelectron depends only on the frequency or wavelength of the incident photon. This means maximum kinetic energy of the photoelectron depends only on the frequency on the incident light. If the intensity of the incident light radiation is increased, the number of incident photon falling per second on the metal surface increases, but energy of each photon remains the same. This is the law of photoelectric emission. The last one, it is not given here, but photoelectric emission is an instantaneous process. This means the, the liberation of photoelectron, we can consider that the collision between the photon and the electron is completely elastic collision. Completely elastic collision. Therefore, within a no time, that means 10 raised to minus within a minus 9 second, the electron will get liberated. This is the last explanation, and this is the rearrangement of Einstein photoelectric equation. Einstein's photoelectric equation for a maximum kinetic energy K max is equals to h nu minus nu naught. If V naught is the cutoff potential or a stopping potential and E is a charge of the electron, then K max is equals to EV naught. This is the equation we have to remember. We will use this when we are solving the problem. And if nu naught is the threshold frequency of the work function, in the previous equation we have studied phi naught is equals to h nu naught. If we substitute this, we will get this equation. If you want to write this in the form of wavelength, then lambda is a wavelength of the incident radiation, and lambda naught is the threshold wavelength of the metal surface, and c with the velocity of light. Then this equation is converting into E V naught is equals to K max is equals to h into bracket c divided by lambda minus c divided by lambda naught. Thank you for watching my video. Don't forget to like and share and subscribe.